Okay, so today we're going to still talk about the equilibrium constant Kc. Remember, it can also be Kp if they're all pressures and it's given to you in atmospheres. But regardless, we're going to talk about the equilibrium constant as compared to something called the reaction quotient, which is Q. Okay, it's going to be calculated the same way, products over reactants, but it will be, you do not know if it's at equilibrium. So you're going to compare Q and Kc to each other to see if the reaction is at equilibrium or not. And if it is, then they're equal to each other. If it isn't, if one is larger than the other, I'm going to do examples of what to do and what that means and how it shifts, okay? So this first one, here's our reaction. We have H2 plus I2 is in equilibrium, supposedly, with 2HI, okay? And we know that Kc equals 60. That's our given value, okay? And then it says, is the reaction above at equilibrium when the concentrations are as follows? So if these are my concentrations, I'm gonna write an equilibrium constant expression, plug these concentrations in, and see what number I get. If I get exactly 60, I will know that it's at equilibrium, okay? If it's not, I'm gonna show you what happens as far as shifting goes in order to restore the equilibrium, okay? So we have let's go ahead and write our equilibrium constant expression first. So we have Kc equals, now all of these are gases, so they can be included in the equilibrium constant expression. So we're gonna have the products over the reactants. So we're gonna have Hi squared over H2 times I2. Okay, and I know I'm using brackets. You can use brackets or parentheses. It doesn't matter because you're just finding Q. Okay, this is for the equilibrium constant expression. Okay, when I find Q in just a second, you're gonna see that I'm gonna use the parentheses because we don't know if it's at equilibrium yet. Okay, so this is my equilibrium constant expression. Okay, and then Q, which is our reaction quotient, it's gonna be the same kind of thing. Okay, so it's still gonna be the same thing. It's gonna be Hi squared over H2 times I2. And the H2 and the I2 don't get any numbers because these numbers in front are 1. Okay, so now I'm going to plug in the numbers. So I have Hi's concentration as 0.010, and I'm going to divide that, I'm going to square that, sorry, and then I'm going to divide that by 0.010 times 0.010. So if you'll notice, all three of these concentrations are the same. So we're trying to see if this system is at equilibrium when all three concentrations are equal to each other. Okay, so now I'm gonna plug this into my calculator and see what we get. Remember, if we get 60, if we get the equilibrium constant, that means we're at equilibrium. But if we don't, I'm gonna show you how it's gonna shift and what that means. Okay, so I'm going to type in 0.010 squared divided by 0.010 divided by 0.010. Okay, and what I got, if you realize, 0.010 squared divided by this number here is that. 0.010 squared divided by this is squared. So basically, you should realize that Q equals 1. Okay, so to be at equilibrium, your Q and your Kc must be equal to each other. Okay, Q is your reaction quotient. This is, I don't know if it's at equilibrium, let me see. Okay, so Q is 1 and Kc is 60. Okay, so right now, Q is smaller than Kc. Okay, Q is smaller than Kc. Okay, and when that happens, that means the reaction needs to turn reactants into products okay? When Q is smaller than Kc, that means the reaction is not at equilibrium and we need to turn more of the reactants into products, okay? So in order, basically the forward reaction is favored. That's my abbreviation for reaction. Okay, so if I am favoring the forward reaction, the shift is to the right. Okay, the shift is to the right. When Q is smaller than Kc, that means the reaction needs to turn some of these reactants into products, okay? The reactants have too much. All right, so some of them need to be made into products, which means the forward reaction is favored, and therefore it will shift to the right. Okay? So now let's do the same kind of thing. We have the same exact reaction. Kc is still 60. Now we have different concentrations. So let's see if these concentrations are at equilibrium. Remember, if they equal the equilibrium constant, that means the reaction concentrations given are for equilibrium. Okay, so our equilibrium constant expression again is the same as before, HI squared over H2 times I2. Remember, the reason I'm using brackets here is because with the Kc, I know this is at equilibrium, okay? But right now, I'm going to do the same thing for Q, and I'm going to have HI squared over, notice my lack of brackets, H2 times I2. And now I'm going to plug in the new concentrations. So my HI concentration is 0.300, and I'm going to square that, just following the little reaction quotient, which is very similar to the equilibrium constant expression, okay? And then I'm going to divide that this time by 0.010, so that H2 stayed the same, and I2 is now 0.150, okay? So now I'm going to type in 0.300 squared divided by 0.010 divided by 0.150, okay? So if you look and see, I got exactly 60. So Q equals Kc. So when Q equals Kc, that means the reaction is at equilibrium. Okay, remember Q is your reaction quotient. That's what it's called, okay? When that equals the equilibrium constant, that means the reaction is at equilibrium. These concentrations are the equilibrium concentrations for this reaction, okay? These were not. Even though the concentrations themselves were equal, when I plugged them into the equilibrium constant expression, the number it gave me was less than the equilibrium constant that was calculated, which means I needed to shift to the right, okay? Let's try same reaction again, see what happens. Okay, now that we know that that second one was at equilibrium, if we look here, our concentrations aren't the same as they just were. So we already know it's not going to give us 60, but let's see what does happen. Okay, so our equilibrium constant expression is still the same, HI squared over H2 times I2. So our Q is the same, HI squared over, H2 times I2. Okay, sorry, I accidentally drew a bracket there. Okay, so I'm going to plug in these concentrations now. So I have 0.100 squared divided by 0.100 for the H2, and then times 0.0010 for the I2. Okay, so 0.100 squared divided by 0.100 divided by 0.0010. Okay, so this time I got 100. So Q equals 100. Okay, and Q this time is greater than the equilibrium constant. Okay, so for our first one, the reason why I kept the same reaction is so you could see the comparison. Q was less than Kc for the first one. Q equaled Kc for the second one, where it was at equilibrium. This time, Q is greater than Kc, okay? Which means my reaction needs to turn products back into reactants, okay? Which means that the reverse reaction is favored. Reverse reaction is favored. Okay, so in order to make more reactants, I'm going this direction. So this time I'm going to shift left. Okay, so to sum it up, when the reaction quotient Q is greater than the equilibrium constant given, the reaction needs to make more products, so the forward reaction is favored, which means it shifts to the right to restore equilibrium. When Q equals the equilibrium constant, that is at equilibrium. Those concentrations are at equilibrium, okay? When Q is greater than Kc, or the equilibrium constant. We need to turn products back into reactants, which means the reverse reaction is favored. Therefore, we will shift to the left. Okay, so a lot of your calculations will be writing the equilibrium constant expression, identifying what Q is, and then comparing it to see if it's greater than, less than, or equal to.